Hi everyone, I'm Lin Chen from Nanjing University. I present our work impact analysis of cross-project bugs on software ecosystems. I introduce our work from these aspects. Recent years have seen a trend that software projects are forming large-scale social-technical ecosystems in which projects depend on the infrastructures or functional components provided by other projects. For example, SciPy is an upstream library in the scientific Python ecosystem and has a significant number of downstream projects dependent on it. Here, we call bugs found in a project which affect many other projects in the ecosystem through interdependencies, cross-project bugs. In our previous investigation, we found that more than 17% of bugs are cross-project bug ones. On average, most of these bugs have wide impact on other projects. For example, this NumPy bug uh, affects more than 20 downstream projects. Another example comes from SciPy, a famous Python scientific computing project. Bug found and reported. Fixing the bug lesson requires changing the output interface and hence might break some downstream projects. A SciPy developer thought that if they fix the bug in the upstream project, some downstreams, for example, Psyche image, will break. Then he asked downstream Psyche image people for feedback. However, after a lengthy inspection of their code, Psychic Images developers reported that there is no use of the bug method that satisfies the failure triggering conditions, and hence the bug may not concern their project. Still, Psychic Image developers provide several suggestions, and the bug was eventually fixed after lengthy debate. Then the bug was fixed. Unfortunately, 6 months later, a developer of Newland reported, and they complained they fixed since it broke their code without any warning. They spent much effort in debugging the problem tracing back to the problematic fix. The real-world example discloses that it is difficult to provide an appropriate fix if the upstream and downstream sides are unclear about the possibly affected downstream code before starting to design a fix. So we say that to provide a satisfactory fix, the upstream side have to identify the affected downstream projects in order to communicate the proper person for frustration. The downstream side needs to identify which parts of things are affected in order to provide suggestions and work around the bug on an early stage. So our objective is an ecosystem-wide bug impact analysis to identify the effective downstream models of a given upstream bug. And we face two challenges. The one is that which downstream models are using the upstream bug method to deal with this problem, which concern lack of ecosystem-wide interdependent inter-project codependencies and scalability and version sensitivity. The other problem is that which downstream uses satisfy the bug-inducing preconditions, and which concern the efficiency and the complete coverage. This is an overview of our method. For each model, all statements and the defect trigger conditions from the entrance of the model to the call point are encoded into symbolic constraints, and the constraints are solved to determine whether the model is affected. Our framework contains two parts: ecosystem-wide dependency analysis and the intramodal impact analysis. The first part is an ecosystem-wide dependence analysis. The goal of the ecosystem dependence analysis is to construct a version-sensitive dependence network over the target ecosystem, which is accomplished by the dependence analysis and the version handler. Within the target ecosystem, each project is processed independently to better handle the dynamic evolution of the ecosystem and to achieve scalability. First, for each project with a base version of the project as the input, the dependence analyzer leverages fine-grained function invocation relations to construct a base dependence network. Then the version handler processes successive versions of the project incrementally by comparing function call changes to add version-specific information to the network. Note that while the network is stored as a central database, its construction and update are modular and distributed to individual projects. Hence, when a project is updated, only the dependencies related to the project may be updated. Such a design substantially reduces the maintenance overhead. Given an upstream bucket function, the model selector can easily identify the candidate downstream models using the dependence network. The second part is an intramodal impact analysis. The intramodal impact analysis takes three resources as inputs. That's individual candidate models, a bucket upstream function, and the failure-inducing precognitions extracted from bug reports. It analyzes each candidate and identifies whether the candidate is truly effective. We say a model is truly effective if with some legitimate inputs to the model, the bug in the upstream function can be triggered. Specifically, the intramodal analysis consists of three subcomponents: the code preprocessor, the constraint encoder, and the SMT solver. The code preprocessor reduces code with rich syntax to a simple form. We analyze three failure-inducing preconditions: type, value, and property. The constraint encoder symbolically encodes paths to the call size of the upstream function, as well as the failure-inducing conditions. The constraints are then passed to the SMT solver. If it is satisfiable, the analysis model is considered effective. Our evaluation aims to answer two questions. The first is how effective of our method, and the second is how efficient. Our database includes 31 cross-project bugs with NumPy and SciPy as the upstream projects, involving 22 projects with 121 versions. Here is the result. First, there are more than 25,000 candidate downstream models, and after analysis, there are only 1,132 effective models. That means that we prune more than 95% of the candidates, and the average precision is about 92%. And here is the efficiency. The most time-consuming part is the dependency analysis. It takes about 50 hours. And the intramodal impact analysis takes only less than 1 second on average. And the conclusion, our objective is for given cross-project bugs, identifying the effective downstream models. We have two contributions. One is an ecosystem-wide cross-project bug impact analysis method. The other is an aversion-sensitive cross-project dependency network construction method. Thank you.